You step out of the shower, and an hour later, your hair is dry. An athlete finishes a marathon completely drenched in sweat, and by the time they have cooled down, their skin is bare. Or consider laundry hanging on a clothesline on a breezy Tuesday afternoon. After a few hours in the sun, the water trapped in the fabric simply vanishes. In school, we learn that liquid water turns into a gas when it reaches its boiling point of 100 degrees Celsius. But a damp t-shirt on a clothesline never gets anywhere near that temperature. So how does the water escape? Liquid water doesn't require a stove to become a gas. It transitions continuously, right at room temperature, through a process called evaporation. We usually don't notice it happening because true water vapor is a colorless, invisible gas. It is distinct from the cloudy mist hovering over a boiling kettle, which is actually just tiny droplets of liquid water we incorrectly call steam.
This molecular escape act provides the physical foundation for how our bodies stay cool and how the Earth regulates its entire climate system. To understand how water escapes without boiling, we have to look at what temperature actually is. In physics, temperature is a measurement of kinetic energy, the physical, bouncy movement of microscopic molecules. This diagram shows a microscopic cross-section of liquid water. The molecules are in constant motion. Dialing up the heat translates into faster, chaotic bouncing. Evaporation happens strictly at the surface. Bumped from below, top-layer molecules break their bonds and launch into the air. This quiet, surface-level exit is very different from boiling. Boiling is a rapid, forceful conversion happening throughout the entire volume of the liquid, creating large bubbles of gas that push up from the bottom. We can speed up this quiet escape by changing the environment. Raising the temperature gives the molecules more energy to break free. Increasing the wind speed clears away the humid traffic jam of escaped vapor sitting right above the liquid. Spreading the water over a larger surface area provides more exit points for those top-layer molecules. And if the surrounding air has low humidity, meaning it is dry, it acts like an empty sponge, eager to absorb more vapor. By manipulating these 4 specific variables, temperature, wind, surface area, and humidity, we can predictably control exactly how fast a puddle or a wet t-shirt dries up. This transition comes with a strict energy cost, known as the latent heat of vaporization. As the liquid rapidly evaporates into the air, it physically drains heat away from your skin, leaving you feeling cold. Long before modern refrigeration, human engineers harnessed this biological cooling mechanism to preserve their food and water without electricity. They built porous clay containers, like these traditional earthen makas. Water slowly seeps through microscopic pores to the outer surface of the clay. As that water evaporates into the hot air, it steals heat from the pot, keeping the contents inside significantly cooler than the surrounding environment. Evaporation serves as a global thermal transfer system, an invisible engine that protects our biology and preserves our resources by pulling heat away from where it's not wanted. Once those billions of heat-stealing molecules escape into the air, they enter a planetary-scale recycling system. They join a massive upward migration of vapor rising off the surface of the oceans and the moisture exhaled by global plant life through transpiration. Transpiration is the process where plants release water vapor into the air through tiny openings on their leaves. This animated diagram tracks the journey. Warm, moist air carries vapor upward. As it climbs, the atmosphere becomes progressively colder. The vapor cools, turning back into liquid by clinging to condensation nuclei, tiny airborne dust particles, pooling together to form the liquid droplets we call clouds. As more vapor condenses, these suspended droplets merge. Once they become too heavy for the air to support, gravity pulls them back to the surface as rain, snow, or hail, a process known as precipitation. And suddenly, a dry city street is flooded. The water that quietly vanished from a clothesline or an ocean miles away has returned. This runoff flows into street drains, replenishes underground aquifers, and feeds rivers. Soon, that same water will be warmed by the sun, ready to evaporate all over again. Since only 1% of the water on Earth is fresh and accessible for human use, this molecular journey is our only source of replenishment. The water in your glass today is the same water that quenched the thirst of dinosaurs 65 million years ago, making the preservation of this finite, recycled cycle essential to our own survival.